One of the leading platforms right now is superconducting qubits, which are great, but they're very difficult to interface them with light. So if you want to create a quantum network, you need something to convey this information. And the best thing we know so far is using photons.
The word foundry might make you think of large machines pouring metal into molds. But Argonne National Labs has a quantum foundry that implants individual atoms, like silicon, into materials such as diamond. The resulting spin qubits are optically active and can use photons to communicate. We can expect spin qubits to help interconnect systems, which could help us achieve distributed quantum computing, but they also could be used for everything from room temperature biological sensors to durable space-based dark matter detectors. Let's explore that literally cosmic range of applications in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the Assistant Staff Scientist at Argonne National Laboratory, Benjamin Pingault. Welcome to the show.
Thank you for having me.
Yeah, this interview has been a while in the making. It took so long to get someone from Argonne that you weren't even there when I started trying to get someone from Argonne to come on.
Welcome to National Labs.
Yeah, it takes forever. So I visited there. This is going to air roughly almost 3 years to the date from my visit on site. And that's how long it was like back and forth with getting approvals and everything. But and then you happily joined the organization and here you are. So I want to talk a little bit about your work because obviously Argonne's a whole big beast. So let's start a little high level. What are spin qubits? How do they differ from other types of qubits, and what that basically sparked your interest? Like, what sparked your interest about them?
Yeah, so spin qubits are a little bit like tiny magnets in the solid state. Mostly, they can be pinned to an individual atom or a bunch of atoms, and they obey the rules of quantum mechanics. So they can be in several states at the same time. They can be entangled with one another. And the reason why I got interested in them is that they really are at the junction of several fields of physics, because you have a lot of, so the spin control itself is mostly microwave control, complex pulses that have been developed for NMR, for example. They are at the junction with optics, because a lot of the spins that I'm interested in are optically active. So we use laser pulses to initialize the spin state, read it out, sometimes for controlling it. They're also at the junction with atomic physics, because they're pretty much single or few atom systems. And they are at the junction of solid state physics, because they're being hosted in a solid state matrix. So they interact with all the stuff that you can find, all the mess you can find in solid state, with other spins, with phonons, with charge traps, and everything we can blame when we're not seeing what we want to see.
So when people are trying to visualize the actual modality of spin qubits, like what they exist in, if you hear about the other ones, you know what they are. Like trapped ions, they're ions, right? They're superconducting is a Josephson junction. What exactly are these being created physically out of in your case?
So in my case, I'm working mostly on spins in diamond and in silicon carbide.
Mm-hmm.
So the way to create them, there are many ways, but the way we usually use is by implanting. So for example, for one color center that is called the silicon vacancy center, we shoot silicon into the diamond using an accelerator. And that creates a few vacancies, and then we anneal, and the vacancy will confine the silicon atom. That's pretty much in a nutshell how we do it.
So it's not like you're looking for something, you're creating it, right?
We're creating it. And that's important
like...
for quantum technologies, because you want something that is scalable. So you need to have control over it.
Okay. So you're able to make a lot of these close together. Is that the idea?
They can. The most important part is actually to be able to introduce them into nanostructures, because all of the systems needs to be integrated. Ideally, we would like to have a chip with all the necessary microwave, electrical, and optical connections that we need, because they're active optically. So we want to take advantage of that and use the photons that those systems emit for quantum technologies and quantum networks in particular. So what you need is to have those color centers as we call them because they emit light, have those color centers integrated into nanophotonic devices, so such as photonic crystal cavities, for example, which are pretty small, like a few hundreds of nanometers to a few microns. And then this way we can extract the photons most efficiently. And so the idea is that ideally, you want to create just one of those color centers right at the best spot of your photonic crystal cavity and be done with it.
So you would be creating them and then putting a bunch of these, just so people could visualize, would be a bunch of little tiny elements that you're creating and then moving them close together and some kind of grid surrounded by the control electronics. Is that the dream setup ultimately?
Yeah, so you can imagine a chip with rows and rows of nano beams
Hmm.
with small holes in them that form the photonic crystal. And at the center of each of those beams, you'll have one color center.
Hmm.
And on each side of the beam, each side of each beam, you have like a microwave line, for example, and maybe a couple of electrodes. And on the edge of the chip, you'd have plenty of optical fibers glued to each of the photonic crystal cavities, each of the small beams. And this way you can talk to many of them at the same time. You could even imagine something even more integrated where the beams are actually connected to an on-chip photonic circuit. So a little bit of racetracks for photons that would make photons interact with one another, change their state, delay them, or change their polarization, change their frequency, for example, all this on chip.
So a couple of benefits here to this type of approach. One is, does this operate at room temperature?
Unfortunately, not.
Not?
We
Okay.
wish it were, but it's not. It's not the main issue, to be fair, because most of the platforms actually require a significant amount of equipment, whether it be cryogenics or complex trapping mechanisms for atoms, for example. There are some proposals to use some of the color centers at room temperature.
Hmm.
The issue is that at room temperature, it's usually more difficult to read their spin state reliably.
Yeah, I was gonna ask because I had read that, so that's why I was asking about the temperature. Yeah. So you're focused more on getting the higher fidelity of the qubit accuracy, and is it longer coherence time then, if it's the refrigerated type?
Typically, yes, because when you operate below, say, 4 Kelvin or even closer in the millikelvin range,
Hmm.
everything quietens down in the solid state matrix. So you have much more control over what's happening, especially at the quantum level, because a lot of phonons that can interact negatively with your system will not be populated, so they will not be there. You have a lot of charge traps and general dynamics happening in the solid that will also be considerably reduced.
Okay, so to help all that coherence and minimizing of noise, obviously you have to figure out the correct number of these to put on one chip, right? Because you have the control circuitry that just adds noise, that adds interference. So, do you have any guesses around what you think you could squeeze onto one little chip yet, or is it too early?
I mean, it depends really on what you want, because those spin qubits can be used also for sensing, and then you can have ensembles. Actually, a lot of things are done with the NV center, for example, in Diamond. A lot of the sensing is done with ensembles, so you could have millions, billions of them if you want to. If you want for more quantum computing or few control over a few spins, then it becomes a little bit more challenging. Because as you said, you need control over each of them. And it doesn't really scale nicely if you start going into the millions because you have a lot of connections.
Hmm.
But the way you can handle it actually is sometimes you need control over one of them and it will control its environment. So, for example, what we use is neighboring nuclear spins. So nuclear spins attached to, say, carbon-13 in diamond, for example, has a nuclear spin. And so we can use the spin of the color center to control neighboring nuclear spins that will have very long coherence times and can be used actually to store information or even process information using just this entry point that is the spin of the color center.
So this isn't just intended to be a quantum computer. Obviously, you're envisioning it to be sensor, potentially quantum memory, that kind of thing.
Quantum memory and also interface. Because, for example, one of the leading platforms right now is superconducting qubits,
Hmm.
which are great, but they are not, they're very difficult to interface them with light. So if you want to create a quantum network and you want to transfer information from one system to the next on short distances or long distances, you need something to convey this information. And the best thing we know so far is using photons. So the idea would be to interface superconducting qubits, if that's what the platform we want to use, with one of those or several of those color centers, transfer the information from the superconducting qubit to the spin of the color center, and then transfer to photons emitted by the color center.
Okay. So this would, in a sense, enable like repeating too, possibly?
Yeah, quantum repeating. Although for quantum repeaters, most likely you wouldn't need the whole superconducting qubit interface. You probably have enough spin qubits on chip to do that. Obviously, it depends on how you want to scale it up. If you want to go into the gigahertz range for exchanging information, then you might find it a little bit challenging. But so far, yeah, you have right now enough spins on a chip to do something reasonable.
So when we're thinking why this is all being built, Argonne has the Quantum Foundry, right, which came online around the time you joined. And what's the basic mission of that of Quantum Foundry?
It's very much an interface because Argonne is very good historically and still nowadays with material science.
Mm-hmm.
And so the idea is that quantum technologies have developed a lot of basic principles for a lot of the qubit platforms, but now they need to improve them so that it's actually something you can use for actual applications. And materials are a huge part of this. You cannot just rely on a hero device that works once and you publish your PhD on it. You really need to have something that is reproducible and that you can scale up and produce. So the aim of the Quantum Foundry is to interface between materials engineering and the needs of quantum technologies. So what we do typically is we'll produce, say, grow a diamond, implant it with the color centers we want, and then check the properties of the color centers. Do they have good optical properties? Do they have good spin properties? Do they have a lot of noise or little noise? Do they have accessible nuclear spins that we can use in quantum procedures? And then we feed that back into the growth, saying like, okay, the optical properties were not great. We probably had a lot of charge traps. Can we try a different type of growth to try to minimize that? And this way, with this feedback loop, fast feedback, because literally I'm working with the people growing the diamond, we can improve materials much faster. Because typically in academic collaborations, you have a grower you are collaborating with, they're collaborating with many other people. So you'll get a sample every few months, maybe, depending on their bandwidth. And they can't just optimize for you, they need to optimize for other people who are asking something maybe slightly different. So having this close collaboration with the growers, me being more on the measurement side, is very precious.
So this is going to sound like a weird question, but basically, Taiwan has mastered creating silicon, right? I mean, they're just they when it comes to chip manufacturing, it's hard to beat them. Is there some like extra motive here in making the Quantum Foundry able to master some new level of fabrication for the future? So that way, like we have a leg up in the US or in like Chicago area for like developing practical implementations of these devices, like constantly refining them. You know what I mean? Like boosting the technology of building them better also in addition to just developing a one-off machine like or a hero device or something.
Yeah, I mean, for now, it's still very much open science. We publish all the
Mm-hmm.
results we have, so it's closer to an academic endeavor still,
Mm-hmm.
even though we do have interfaces with industry. But yes, let's say that's the seed of building US-based capacities for quantum materials and the building blocks for quantum technologies.
At some point, it might go a little closed, right? It's possible.
At some point, well, the thing is, national labs are not supposed to pick winners. So as soon as it gets into really industrial production, this is pretty much where our work stops,
Okay.
and we'll focus more on still research aspects of it, because when you're scaling it up, you focus on engineering issues and integrability, cost, etc. Whereas national labs will try to work more fundamentally on improving the platform.
Yeah, because even though we touch on silicon in certain device types of devices, certain room temperature machines or whatever, and other control circuitry, we are, to be clear, building a new industry. It's
Yeah,
like from
very much
scratch,
so.
basically. So you got to wonder like what will repeat from the past, and what kind of extrapolations we can make about what will be valuable to the world. In addition to having the machine, having the ability to refine the machines and make them for other countries or whatever, these kinds of questions are going to pop up.
Yeah, I mean, it's really like Illinois is really well positioned for that kind of things because there is a strong industrial base, there's a strong research base with major universities in the area, national labs also. So, and now industrial partnerships. The governor inaugurated recently this big area in the south of Chicago where quantum industry will establish a few of their
Yeah.
facilities.
Yep. Quantum's working there too, and yep, it's going to be quite a hotbed or cold bed.
Yeah.
Yeah.
Not everything is cold. Not
Yeah,
everything
not
is cold.
everything, but a few things. So, what types of sensing applications do you think this would be best suited for if it went out into the real world?
Yeah, there are a lot of things. So for the nitrogen vacancy center, for example, in Diamond, a lot of applications are in biology because this one works at room temperature. So a lot of biology applications are currently being developed, potentially for medical devices, including. So, for example, detecting heartbeats using those sensors. One advantage is that they're very, very small,
Hmm.
right? It's a few atoms. So your limitation is how small you can make the electronics around it.
Yeah. And temperature, like you said, the human heart, we probably don't want it to be 0.15 millikelvin
No,
at
so
any
the
given
NV
time. It's
Center,
probably not a good idea.
yeah, the NV Center is perfect for that. Then other things include in situ diagnostics on electronics chips, for example, because they can sense currents or magnetic fields. So if you've got some leakage current somewhere on your chip, you could potentially use them to say like, okay, this is where the leakage is happening. You might also use that for characterizing devices. If you've got some magnetic parts, like right now we're recording a lot of materials using magnetic encoding, you can use those sensors to sense those magnetic fields, sense this information that is being stored. So you could envision some denser memories. You could also, in the field more of quantum technologies, use them as sensors inside another quantum computer or quantum device. And then you could use that for at low temperature because your computer might be anywhere at low temperature. So you'd have a little bit more freedom to choose the platform you want to use for the sensing. And then for fundamental science, even, there are some proposals to use such color centers for dark matter detection.
Yeah, I was going to ask you about space-based applications. Yeah. Would you visualize that being put on in out in space in some kind of dark matter detector or buried deep into the earth, that kind of thing?
Both.
Both? Yeah.
The advantage of space is that it's already cold,
Yeah.
so
3, 4
no problem.
Kelvin. Yeah, it's not bad.
Exactly, no problem with that. And again, they're pretty simple systems,
Hmm.
so the payload wouldn't be very high. So you could use that, yeah, as a diagnostics means in a satellite, or even potentially for quantum communication via satellites, or for quantum sensing also. And same thing inside the Earth. You have a platform that is pretty. It's solid state. It's diamond. It's not really going to go anywhere. So what's sensitive is what you're putting next to it.
This is what quantum science needs right now. A good boost for newsworthiness would be if we figured out if dark matter is real, if Mond is real, or whatever. Like if that would be definitely a good boost if we could be responsible. But they're durable, right? Like if this was on a rover on Mars, or if this was part of like the space-based LIGO, I guess it's called LISA, I think, where they're going to be developing something like that, that'll be more durable and reliable for years to come, I'd imagine.
Yeah, definitely. I mean, there are in some research groups, they've been using the single same spin for over 10 years.
Yeah, well, that's pretty durable. Yeah. Yeah.
And most likely it's what you put around it that's going to die before. Like, your laser or your electronics might face more issues than the quantum sensor itself.
So, how interdisciplinary is it where you work right now? Like, what kind of input are you getting? Are you getting direct input as you're developing these things to how they can be best applied and what modifications you might have to make in the future for that? Is it already happening, or is it still a ways off? Like, are scientists more focused on space coming to you or whatever? Is it that kind of thing where there's communication regularly?
So since we're more on the fundamental aspect, we focus more on general applications and the properties of the materials. Then if we have some startups that have come out of our groups, so when someone thinks that there's really a promising application, they want to make it a startup, they're free to do it. But that's true that we're just at the junction between the two, between the industrial applications and the research. That's the point of the national lab, really, and the foundry in general.
There's a huge push for networking in the Chicago area generally. I mean, that's like the number one thing that you keep hearing about in that region. The test beds, there are many, many miles of fiber and everything already being dedicated to this. Zeilinger's old work has basically been resurrected for the quantum computing age all over in that area. It's pretty fascinating stuff. So because this technology is good for those interfaces we talked about earlier, I'd imagine there's already some roadmaps being sketched out about where it might be applied, right? With these types of kind of
Yeah, yeah, definitely. I mean, the idea for those networks is that they can actually be used for a lot of things. The obvious one is quantum communications,
hmm
but then even for distributed quantum computing. So if you've got several quantum computers, you bring them together, you connect them together, and you get a considerably more powerful processing system.
hmm
Because each time that's the magic of quantum computing, each time you add a qubit, you're actually doubling your processing capabilities. That's in theory. In practice, you have some limitations, but
Sure.
that's the potential. And also for quantum sensing, because distributed quantum sensing is also important. Like not just for dark matter, but if you want to sense some changes in the Earth's magnetic field, for example, that would be very important. For networking, if you want, not so long ago, the plane of the Ursula von der Leyen was denied GPS access as she was landing, I think, in Bulgaria. If you have a onboard quantum sensor that doesn't rely on having GPS access, you won't have to face that kind of issues.
Yeah, we talked to Q Control about that, and I was kind of shocked to learn how many of those attacks happen every single day. It's kind of crazy.
Yeah, yeah.
It's like the number one attack happening when it comes to any kind of subterfuge that's going on. Do you have any insight to the path forward when it comes to networking, like the hurdles with speeds and security and all that? Like, is there anything that this will help further or improve? The whole idea of interconnect, is this going to somehow revolutionize that?
Yeah, I mean, there are many, many ways things can go. Right now, one of the difficulties for networking things is the speed, indeed. Right now, the best quantum networks, long distance quantum networks, are more in the Hertz regime.
Yeah, it's
So,
painful.
back to pixel by pixel
Yeah,
uploading of your
so
pictures.
painful. Yeah. Dial-up modems on a Commodore 64, pretty much.
Exactly, exactly.
Yeah.
So there are a lot of efforts to multiplex, to increase the bandwidth of those systems, to make sure that you can actually interface quantum modules in a meaningful way. Because otherwise, you might be just better off using classical channels.
Mhm.
But if you want to untangle systems and they're long lived enough, even if you're in the Hertz regime, you can still get something out of it. You're not necessarily looking at using a quantum network for watching Netflix.
Yeah, yeah,
Applications would be quite different.
yeah.
So for now, it's still okay. There's a lot of improvements to be made in the control of the material, because sometimes a lot of the delay is just checking that your qubit is ready to be entangled
hmm
and trying the entanglement many times until you get confirmation that it succeeded. So a lot of this preparation can be helped by solving some of the materials challenges.
So, what is the biggest material challenge right now? You think what's like if your team has something that they're going to focus on most heavily this year and into next year, what would you say that is?
If it was just 1 year,
Just like the next thing that you're sort of like directed towards, like to try and improve and see how you can.
it's multiple things at the same time, because we need to optimize many things in one go. We can't just focus on one aspect. I'd say the ideal would be I can put a spin exactly where I want with exactly the other spins around it that I want and nothing else around. No charge traps, no extra spurious impurities, no defects on the surface, because surfaces are absolutely terrible for quantum because plenty of mess is happening at the surface. Atoms are moving around, charges are moving around, spins are moving around. You don't want anything moving around for quantum. So working on those aspects is the most important. And so you've got some surface science, you've got some growth, you've got some implantation capabilities, you've got some control protocols to make sure that you're more resilient to surrounding noise. So many things need to come up together.
So that's interesting. Is there a whole stack of sorts dedicated to just this component that you could think of as running in parallel to anything else that goes on in the quantum computing stack in general? Like, is it software? Is there like other kind of control factors with the electronics involved, like a deep technical stack like that?
I'm not sure I get your question.
So like software that might be involved in helping control the circuitry, et cetera. Like, is there like a software layer?
So yeah, definitely there has been a lot of progress on that. Like when I started working in this field, like 13 years ago, we had to code everything ourselves pretty much, and using whatever data acquisition card we could get on the computer. There were a few systems that we could use to control pulses, like arbitrary waveform generators, which were amazing and they're still used today, but they are not necessarily the most flexible system when you're dealing with a lot of qubits, because they may run out of memory pretty quickly, actually, when you're doing complex control sequences. So now there has been a lot of companies that have developed electronics tools to help us control qubits in a much more efficient way. We don't need to code everything ourselves. It's already part of this is already coded, and we don't need to deal with that. There's a lot of improvement also with lasers. It is very difficult to find good lasers in the visible range that can be tunable, because a lot of those color centers have slightly different wavelengths. If you want to use different types of color centers, you need a whole range of wavelengths you can excite them with. And so that can make things a little bit challenging if you need a different laser for every single one of them. So those have been the hurdles. There is a whole lot of classical technology that needs to be developed for quantum technologies to really be possible.
And one last thing I wanted to dig into for a second. So this whole concept of AI for quantum, how can AI improve quantum computing? Has that touched your field yet? Has AI in any way, shape, or form made this process more efficient? Helped figure out better ways to interact with like lasers or whatever? Like, has it analyzed papers for you and found something that you missed? I don't know. I'm just curious if any of this is starting to filter into these sort of like side projects in the quantum computing world.
There's a lot of push to combine quantum and AI right now.
Hmm.
There are definitely some progress being made now. So typically what can happen is if you have a lot of qubits you need to characterize, it's usually very tedious. You look at the optical properties, you look at the spin properties, you try some
Hmm.
control sequences, etc. Now we can use AI to do that. It will be much faster and start sieving through the bad ones and keep only the good ones, or sieve through specific properties we want to see, depending on the application we want to do. And so we don't need to spend like days in front of the computer doing that. There are also pushes to develop AI tools to fully automate an experiment, not just doing the pre-characterization, where an AI controlled robot can start characterizing different chips and telling us, okay, this one is good, this one is bad, or trying to tweak some of the parameters of the control. We're using also AI to interpret data. So when we use a sensing protocol, just use an AI algorithm to actually extract the relevant quantities we want to know. It's like, well, we're coupled to that many spins and the strength of the coupling is that much. That's really helping, because otherwise you need to do all of this by hand. What's worth noting is that a lot of this is not necessarily AI. There are a lot of Bayesian inference that are more classical systems, more streamlined systems that can also be used and are pretty much as good as AI. AI is one of the tools,
Yeah,
but I think we need to be careful not to use AI for the sake of using AI.
yeah, you don't need AI to update priors necessarily.
Yeah.
Yeah, yeah. It's like, this chip sucks. That's my prior, basically. No, that's great. Yeah, I suspect we're going to see AI in the stack like that in everything and on all aspects of quantum, just that whole AI for quantum thing. And I think it's a fair use.
Yeah.
It's not about like taking people out of the process or whatever. You know, why wouldn't you want to like sift through data much faster? We do that now, as you said. So
I mean, just comparing to how things were done before, we had at some point you need to build your lasers yourself.
yeah,
But then
yep,
once companies started building lasers, that didn't make researchers redundant. They've just moved to doing something else. And now we're asking companies, can you make better lasers for us? Same thing with the electronics. So it's a tool, and we'll just make our life easier, and we can focus more on the science.
yeah. This is where you could be comfortable using the words AI and lasers within a few seconds of each other, and people aren't thinking about the end of the world. Yeah. Yeah. So on that note, yeah. Thanks for joining, Benjamin. I really hope to see this continue advancing, especially because of all the networking impacts it's going to have in the region. And I really am excited at the concept of having quantum computers linked together so they can act as one bigger monster in the future. So thanks for everything you guys are doing there.
Thank you very much for having me and giving us the opportunity to broadcast a little bit what we're doing in the lab.
That does it for this episode. Thanks to Benjamin Pingault for joining to discuss Argonne's work at the Quantum Foundry. And thank you for listening. If you enjoyed the show, please subscribe to Protiviti's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protiviti. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protiviti.com or follow Protiviti Tech on X and LinkedIn. Until next time, be kind and stay quantum curious.